Welcome. In this video, we are going to implement the great paper density estimation using Real NVP from 3 brilliant researchers. If you know a bit about density estimation, you of course know the first author. He authored a lot of papers on normalizing flows as well. The second author, I believe there is no need to present him. He was the inventor of diffusion models. He authored the very first paper that sparked interest in that direction. It was deep unsupervised learning with non-equilibrium thermodynamics that I implemented on this YouTube channel. So I would invite you to have a look at this video if you're interested. And finally, the third author is also a very brilliant researcher. Okay, so by the end of this video, these are the results we'll get. So as always, a self-contained, very clean code that you can run very easily without fighting with dependencies. On these are the results you should expect. Let's dive in directly. We're going to use PyTorch as usual to do the implementation. So let's start by implementing the squeeze 2D operation. So basically what the squeeze 2D operation does, it's just basically what we will call today pixel shuffle or pixel unshuffle. Basically at some point what they do, they trade the spatial resolution. Well, they take this image and they reshape it from left to right. So they reduce the spatial dimension by 2, but then they increase the number of channels by 4. That's what is called today pixel shuffling or pixel unshuffling, depending on which direction you go to. So the squeeze 2D goes from left to right by just reordering the pixels, and we can do the same unsqueeze 2D to go from right to left. Okay, so then what we can implement, it's the checkerboard mask. Okay, so basically that's what is implemented here. As always, I'm just diving into the implementation, not focusing on the paper, but I would invite you to have a read at the paper if you've not done that yet. But basically for Real NVP, in order to be able to compute the determinant of the Jacobian determinant of the transformation, you only modify half of the dimension at a time. Okay, so basically what we do here to keep some kind of spatial pattern, we choose carefully which dimension we modify, on which we do not modify. So basically we apply some pattern. So basically a checkerboard pattern, and we only modify like either the white cell or the black cell. Okay, so we create this mask, checkerboard mask, based on this invert flag. Either we'll only compute the white values or either only the black ones. Okay, and there is the same masking, but that we call channel masking. It's the one on the right. Here we only work with half the channels, so either the first channels or the last ones. Okay, either only the white channels or the black channels on this figure. Okay, so basically now that the checkerboard mask is implemented, we can implement the channel mask. So basically channel mask is very easy. Either we set true to only half the first channels, or we set to true the other half. Okay, depending on this flag first half. Okay, so once this is implemented, in the paper they develop their own batch normalization that's described a bit later. Basically it's a variant of batch normalization where there is no scale, no affine parameters. Okay, so that it facilitates the computation of the Jacobian determinant. That's equation 18. So basically you just need to compute the running average of the mean on running average of the standard deviation that are tracked during training. So basically that's what we track: running mean, running variance, and then at each runs we'll use those statistics that have been accumulated during training. So we can create this private function, compute stats on update. So basically I receive a batch X and I compute the mean on the variance for this batch, and then I update the running mean on the running variance using a moving average, right? We multiply it by the momentum, which is a hyperparameter, 0.9 by default. So basically I'm keeping the old value, but I'm adding the new value with a 1 minus momentum, okay? Okay, and then once this is done, we can implement the fourth pass. So for diffusion model, for normalizing flows, sorry, each layer needs to return the output of the layer, right? But also the log Jacobian determinant of the transform. Yeah, here for some reason we also have a flag that allows not to do that, but usually we want to do it. And we also want to go in the reverse direction. So usually during training we go from data distribution to latent distribution, but during inference we want to go from latent distribution towards data distribution. So basically, if we are training, we need to we compute the running mean under we compute the statistics from the batch, okay, and we also update the running mean on the running variance. But if we are doing inference, we do not compute the statistics from the test data. We use the running mean on the running variance that were accumulated during training. If we are running in the reverse direction, but basically with normalizing flows, all the operation can be inverted. So you can go from X to Y, but also from Y to X. So basically here, either we go from in one direction or in the other. So we implement both. We implement both direction. Or if needed, we also return the log determinant, which is useful for training. Okay, then we can implement a res block. So what is great with this approach of normalizing flows, here again I'm not describing the paper too much, but you have two neural networks, S and T, on while equation 7 and 8 are constrained, so you can only modify half the dimension at a time. The neural networks S and T are unconstrained. They can be anything, okay? So here I can, in my network S and T, I can use res blocks. I can use really anything I want. And I can also use batch normalization in this res block. Here, because we've implemented this batch normalization, we're reusing it. But here we could use any normalization layer. We could also use batch normalization with the parameter gamma on the parameter beta, okay, with the affine parameters. Here we really have no constraints. Later, when we use a batch normalization between layers in our normalizing flow, between coupling layers, we will need to make sure that we can compute the Jacobian determinant. But here we don't need to do that. Here it's really unconstrained. This batch normalization could be anything. It could also be other normalization layers. As they describe in the paper, for the convolutional neural networks, they use weight normalization. Hopefully with PyTorch, it's very, very easy to do. It's just adding one line, just adding a few characters when you instance your convolutional layers. Okay, so then we can implement the fourth pass. So it's just a standard res block, so very easy. And then later we can use this building block in our architectures. Okay, so now we can implement STNet. So what's STNet? It's just basically the neural network that will output S and T based on some input X. Okay, so basically here we are just using a combination of basically it's just a few res blocks with a conv in, conv out, and also convolution just before the output convolution. Here what they mention in the paper, they also use, I'm not sure if they are mentioning it in the paper or if it's in the code, there is this log scale parameter for, we're going to see in a moment what it does. I think it makes training a bit more stable. Okay, so I'm feeding X to my neural network, that gives me S and T. So basically here I'm extracting on one side S, on the other side T from the output of my neural network. And then S should be greater than 0. So one way to do that, for example, is to, for example, we could take the exponential of it, or here we take the hyperbolic tangent. So here we take the hyperbolic tangent of S. To be fair, I'm not sure if S should really be greater than 0. I will need to double check that. I don't remember if there are any constraints on S. But okay, basically here what they do, they take the hyperbolic tangent of S, and they also multiply it by some scaling parameter greater than 0. And basically that's why there is this log scale. They multiply by a scale parameter and they do reparameterization so that the scaling is always greater than 0. Okay, on the log scale is learned. On here they add +1 for numerical stability. Okay, so with our STNet block, so basically now we can implement this full coupling layer. Basically with a neural network, ST gives us S on T. First, the model gives us S, which is unprocessed, let's put it that way. And then we reparameterize S so that it's more stable, and then we return S on T. And now we can implement a neural network that will implement equation 7 or equation 8, depending if we are going in the forward direction or in the reverse direction. So you see, equation 7, we go from X to Y. Equation 8, it's the inverse. We go from Y to X. Okay, so let's implement those coupling layers. So those coupling layers have a mask as input, okay, because the mask will do the partitioning. It will split X in X1 to D on XD plus 1 to D, to big D. So basically splitting the features in X in two groups. And we do that with a mask, either the checkerboard mask or the channel mask. Okay, so we take that into input. Some hyperparameters. Okay, here the coupling layer. When we feed the data to the coupling layer, we need to return the log Jacobian determinant, and therefore in that case it's important to use the proper batch normalization that will give us the that will give us this value that we need. Okay, because otherwise, if we naively apply a batch normalization in between coupling layers without taking into account the log determinants, if we do not take into account the log determinant, results will not be. The log determinant will be used in the loss, and therefore our loss won't be good. Okay, because the batch normalization affects the transform, and therefore its Jacobian is impacted. So we need to take that into account when we do this computation. Okay, just here we're just warping the squeeze and unsqueeze operation into a squeeze class. So basically in the forward direction. So when we go from data to latent space, we want to trade spatial dimension. Well, we want to reduce the number of spatial dimension and expand the number of channel. That's usually what we do for classification, right? We start with a big spatial resolution and we don't scale it. And if you want to do the opposite, go from the latent dimension to the data distribution, we do the opposite, we do unsqueezing. Okay, now we can build our real NVP. So basically now it's just a matter of putting everything together as they describe in the paper. First, well, basically here for now we're just describing our mask that we'll use later. It's maybe easier to have a look at the architecture, and then we'll understand why we create those masks. So basically we start with 3 coupling layers with checkerboard masking. That's what they explain that they do. That's what they do in the paper. Then they do squeezing. So basically that will reduce the spatial dimension. So from 28 to 28 pixel, it will go to 14 by 14 pixel. But therefore the number of channels will be multiplied by 4. Okay, so after the squeezing operation, I have 3 coupling layers with channel masking, and then 3 coupling layers with checkerboard masking. That's what they say in the paper. It's always 3 checkerboard masking, and then 3 channel masking, and then 3 checkerboard masking, unless for the last unless at the end of the neural network it's 3 channel masking and 4 checkerboard masking. That's what we did here. There is something that we do not implement here in this implementation. We do not do the I think they call that Gaussianization. Let me double check the proper wording that they use. So basically this multi-scale architecture, they say they Gaussianize units. We could do that. That will reduce a bit computational cost, but here we're fine. It's a small scale NIST experiment. but we could do that. I'll let you do that, read that and implement it. But without it, it's working fine. It's just that maybe your compute is a bit higher. You use a bit more compute resources. Okay, and then we can implement the fourth pass. So the fourth pass, we just, so basically each of those layers in my model returns the output of the layer, but also the log determinant. So here I'm creating the log determinant. One constraint of normalizing flow is that the input and the output should have the same number of features. So basically the log determinant will have the same shape as X, okay? And basically I go from layer to layer. On for each layer, I get the output on the log determinant, and then I'm adding my log determinant. Because I mean, if I'm just having a look at the determinant, the final determinant, it's the product of all determinants, or in log space, it's just the sum of all of the determinant of each layer, okay? So you can implement for the forward pass or for the reverse pass. In the reverse pass, we just traverse the model, but in the reverse direction. Okay, one last thing for normalizing flow, dequantization of the data and the logic transform are very important. Maybe we're going to discuss that in a moment, but images are just in a way discretized data. They just have, if you are talking about grayscale images, for each pixel you have only 255 possible values. So even if you rescale the data between 0 and 1, data are still discretized, and that creates issue with normalizing flow because you go from a low entropy distribution to a higher entropy distribution, and therefore what's often done in normalizing flow is dequantization, but dequantization you always do that, for example even for classification, and then you also do this logic transform, but all that is it's explained in the paper. Again, we're just implementing the paper. Okay, so once this is done, maybe a last helper we need, a Gaussian log P. So basically for training, we'll map the data to latent space. Then we need to compute the log determinant of the transformation, but also the log probability of the latent Z, and therefore we need this function to compute the log probability. Okay, and now we can finally put everything together and start training. So we create our training data and testing data by calling this load data function from Keras. It will give us the listed data. Then we transform that from NumPy to PyTorch, and we divide the data by 255 so that now data are between 0 and 1. And then we can create a data loader with a batch size of 128. We'll train for 200 epoch on the GPU. We create our Real NVP model. We create our transform logit, and we are going to use the Adam optimizer with a weight decay on 5e-5. I think that's the hyperparameters from the paper. They mentioned that they use weight decay. I don't know if they mentioned the value. Okay, and then we can iterate over the number of epoch. We are going to track the training loss. We iterate for each epoch for each batch. We push the batch to the device, to the GPU, and then we can do the dequantization. Okay, again, even if the data now are between 0 and 1, the data are discrete for now. They are between 0 and 1, but there are only 255 possible values. So we had a bit of noise, of random noise, so that now data are between, well, now the distribution is continuous. Okay, it goes from 0 to 1, and it's continuous. And on top of that, we apply this logic transform, which is explained in the paper. Okay, then we map the data Y to the latent space Z, and then we can compute the loss. So basically the loss, it's the log probability of the noise of the latent plus the log determinant of the model transformation. And here we added an extra transformation because of this logit. So we should also take into account the log determinant of this transform. And then what we want to do is to maximize this log probability. So when we do gradient descent and when we minimize the loss, we take the opposite of that. We want to maximize that, so we minimize the opposite. Okay, then we can do a gradient step. And then we are done with training steps. At the end, we can do the evaluation. So because with this this batch normalization, it's very important to put the model in evaluation mode before doing inference. So we put the model in evaluation mode and we generate 25 images. So when we are done with going from the latent distribution to the data distribution, Y is still in logit space, it's not yet in data space. So we need to feed Y to the logit transform and run it in reverse direction, okay? So basically we go from Z to Y and then from Y to X. X is our data space and then we can have a look at the images. So once we've created our images, then we can plot them. We can create a subplot of 5 by 5 images and then plot each image at a time. Okay, so that's it for this video. I really hope it was helpful to you, that you liked it. If it was, please leave a thumbs up. It's really helpful for helping this channel grow, for me to create better content, and see you in the next video.